He caused this inflation. I gave them a country with essentially no inflation. It's perfect. And it's so good. All you have to do is leave it around. With the skill, with this reading scan, and all of the other money that's being thrown out the window. Caused inflation. The fact is that his big kill on the black people is the millions of people that he's allowed to come in through the border. They're taking black.
Only for students. I don't connect. All the students are not serious. Good morning, class. How are you today? The topic before us this day is radioactivity. Is the last lecture for inorganic chemistry. We'll be having inorganic chemistry for the past 3 weeks. So today is the last lecture for inorganic chemistry, and the topic before us is radioactivity. Radioactivity. Now, you know that our normal chemistry that we have been studying has to do with valencing electrons, the interaction of electrons when electron is transferred from one atom to the another. Sometimes you share the electrons, sometimes one have to lose it, the other one to gain. Those are what is a day in chemical reactions. But when we talk about radioactivity, we are talking about nuclear reaction, the reaction that has to do with the nucleus of an atom. The reaction that has to do with the nucleus of an atom. And so during radioactivity, the major event that takes place is that the nucleus disintegrates. The nucleus disintegrates. So basically, nuclear reaction is reaction that has to do with the protons and neutrons, the nucleus of an atom. And the basic difference between chemical reactions and nuclear reactions is that nuclear reactions involve the disintegration of the nucleus, whereas the chemical reactions involve the redistribution of the valencing electrons. And in nuclear reaction, you have a lot of heat change that usually will take place, but in our normal chemical reaction, the heat change is not as great as the nuclear reactions. And in our normal chemistry reactions, new bonds are formed, new elements are formed, but radioactivity, no new elements that are formed in nuclear reaction, but in our normal chemical, no new elements are formed. What you have is bond breakage and bond formation. And so in nuclear reactions, the external factors like your temperature, volume, temperature does not affect, pressure does not affect nuclear reactions. But in our normal chemical reaction, we have external factors, pressure, temperature, volume, catalysts, they all affect chemical reactions. And now, when radioactive atoms are unstable, because they are please mute, everybody should mute yourself, everybody mute yourself. There's so much noise on the background. Mute yourself now.
I wanted to join one when I switch on my video. My first video, tired video, no one.
Everybody should mute themselves. I don't want noise in the background anymore. I don't want to hear any noise. So the process in which the nuclei of certain elements undergo disintegration accompanied by emission of radiation is what we know as radioactivities. In other words, radioactivity is the disintegration or decay of unstable atoms. And this is accompanied by emission of radiation. It's accompanied by the emission of radiations. And so we have unstable atoms. We have unstable atoms such as uranium, such as radium. They are said to be radioactive. And when radioactive undergo disintegration, we say they are decaying. We say they are decayed. All radioactivity are classified into two. We have the natural radioactivity and we have the artificial radioactivity. The natural radioactivity is the spontaneous disintegration of an atomic nucleus with emission of particles. That is natural radioactivity, the spontaneous disintegration of an atomic nucleus with emissions of particles, whereas artificial radioactivity is an induced disintegration. This artificial radioactivity is induced disintegration, whereas natural radioactivity is spontaneous disintegration. Okay, so the induced disintegration of a nuclei, which is brought about by the bombardment of the stable nucleus of an atom with a high speed of particle, causes the unstable nuclide to undergo disintegration. So that one, we classify that one as artificial integration, disintegration, which is induced. Whereas natural radioactivity is spontaneous disintegration of the atomic nucleus with emission of particles because of instability. And so all these reactions, natural disintegration and artificial integrations, they give out radiations which are classified as alpha particles, beta particles, and gamma particles. And so we are going to be looking at the properties of each of these particles, the alpha rays, the beta rays, and the gamma rays. First of all, let us look at the properties of the alpha particles. Let's look at the properties of the alpha particles. The alpha particles is a helium nucleus. It is an helium nucleus. It contains a mass number of 4 and atomic number of 2. In other words, it contains 2 protons and 2 neutrons. Okay, the mass charge is 4, and that is the mass. The mass number is 4, while the atomic number is 2. Now, take note of this. All alpha particles are positively charged particles, and they move at a very high speed. They move at a very high speed. Okay, they have low penetrating power, as you can see on the table before you. They have a very low penetrating power. They can be stopped by ordinary paper or by a 0.01 millimeter aluminum foil. So they can be stopped by paper or aluminum foil because they have a very low penetrating power. Okay, they can only travel few centimeters in the air. And examples of them, we are going to be showing you example of radioactive reactions that give out alpha particles or alpha rays. So I've said that alpha particle is an helium nucleus. It has a mass number of 4 and atomic number of 2. Okay, it contains 2 protons. The nucleus contains 2 protons and 2 neutrons. They are positively charged particles and they move at relatively high speed. They have a very low penetrating power and they can only travel few centimeters in the air, and they can be stopped by ordinary paper. Now let's look at the beta rays or the beta particles. The beta particles are either an electron the beta particle are either an electron, a fast-moving electron, or positron. You know that the charge of an electron is -1, okay? And you have positron. The charge of positron is +1 for the charge. So positron, which is not common, all that we know about beta rays is that beta rays are fast-moving particles, okay? And the charge is -1. But we also have another beta ray that is also classified as positron, and it has a positive charge. And a positron is a particle identical to an electron. Okay, the difference between positron and electron is that the positron has a positive charge, whereas the electrons has a negative charge. But both of them are typical examples of the beta rays. So the beta rays have more penetrating power compared to the alpha particles. Okay, their penetrating power is higher than the alpha particles, but they are less than the gamma rays. And so penetrating power increases from alpha to beta rays, and the highest is gamma rays. And so they can be stopped by metal, by aluminum foil. Okay, they can be stopped by any metal foil, or an example of a metal foil is aluminum foil. Okay, they have less ionizing power compared to they have less ionizing power compared to alpha particles. Okay, and they can also be stopped by a concrete, by 1 centimeter of aluminum. So any metal foil will stop beta rays. So far I've said that beta rays are either electrons negatively charged or positron that are positively charged, and they have more penetrating power when you compare them to alpha particles, and they can be stopped by any metal foil, and they have less ionizing power compared to the alpha particles. Lastly, let's talk about the gamma rays. The gamma rays, they are high energy electromagnetic radiation. As you can see on the table, they are very high energy electromagnetic radiation. They exhibit wave properties. So they have a short wavelength, and they have very high penetrating power. It has the highest penetrating power among the three rays, the alpha rays, the beta rays, and the gamma rays. The gamma rays has the highest penetrating power when compared to the others. And so they have zero mass. They also have zero charge. Okay, for this reason, most times they are omitted from equations. You don't see them in equations because of zero mass number and zero atomic number, zero charge, zero mass. However, all these radioactive emissions that we're talking about, the alpha rays, the beta rays, the gamma rays, they can be detected using the following instruments. These alpha rays, these gamma rays, these beta rays can be detected using the following devices. They include the Jijamula counter, the scintillation counter, the diffusion cloud chamber, and electroscope. These are the 4 major devices or instruments that you can use to detect alpha ray, beta ray, gamma rays where radiation is taking place, whether natural or artificial. And so the instruments include the Jijamula counter, number 1, number 2, the scintillation counter, number 3, the diffusion cloud chamber, and number 4, the electroscope. Okay, now there is what is called the quality factor of rays. There is what is called the quality factor of rays. The quality factors of rays gives an information about the danger of a particular radiation. Okay, the higher the value, the more dangerous the radiation is. So the quality factor tells you about how dangerous a radiation is. Okay, if the value is higher, then that means that the radiation or the rays, either alpha or beta or gamma ray, is very dangerous, and it is a dimensionless quantity. It has no unit. Now, nuclear reaction involves changes in the nucleus of an atom. And don't forget, in the nucleus of an atom, you have the protons, you have the neutrons. These two form the nucleus of the atom. So basically, the nuclear reaction, like I've mentioned before, is a reaction that deals with the nucleus of an atom. And such reaction usually takes place when the nucleus is unstable and there's a decay. What do we mean decay? When there is disintegration of the nucleus of an atom, okay, by reason of radiation, it will give out rays, radioactive rays. And these rays could be either alpha rays, beta rays, or gamma rays. And so nuclear reaction involve changes in the number of protons or neutrons that form the nucleus of the atoms. This is unlike what you have in our normal chemical reaction. I've explained that before, that in our chemical reaction, it involves either the loss or gain of electrons or the sharing of electrons to form new bonds. Okay, so this is basically the major difference between chemical reaction and nuclear reaction. Nuclear reaction involves changes in the proton and neutrons of the nucleus of the atom. It's a reaction that has to do with the nucleus of the atom, whereas chemical reaction has to do with the valency electrons of the atom, okay, when they are lost or gained, or when the valency electrons are shared. Now, if you see before you, what you have before you there is the nuclear reactions. Examples of nuclear reactions. Okay, so if you look at those nuclear reactions, they involve the bombardment of the reaction with helium nucleus in the first two reactions, and in the third reaction, it involved the bombardment with the neutrons, okay, and the last one involved the bombardment of the helium nucleus. So in a nuclear reaction, the sum of the masses and the atomic number of both sides of the equation must be the same. It must be the same. Now, in balancing of a nuclear equation, listen to me very carefully, it's very important. In balancing of a nuclear equation, the mass number, usually the top number, okay, in the atom, and the atomic number, usually the down number, the number in the down, in the formula of the atom, must be the same on the left and on the right. It must be the same. For balancing to take place, the sum total of the mass number of the reactants must be equal to the sum total of the mass number of the products. The same thing goes for the atomic number. The sum total of the atomic number on your left, which is the reactant, must be equal to the sum total of the atomic number on your right, which are the products. So the mass number, the atomic number of the reactants on your left must be equal to the mass number and atomic number, respectively, on the products on your right. And so that is how to balance the reactions. So usually you balance the nuclear reaction with the appropriate radioactive emissions. And the radioactive emissions could either be alpha particle, beta particle, or gamma particle. So if you look at the reactions before you, you will find out that the addition of the mass number on your left is equal to the addition of the mass number on your right. The same thing with the atomic number on your left and the atomic number on your right. So in balancing the equations, what will be given out will either be any of these rays or particles that I've measured about. And before now, I also stated that you can detect or measure the rays that are being given out using some devices in the laboratory. And I've measured the Jamula Cantor, I've measured scintillation Cantor, I've measured the cloud chambers. Here we also have addition of the bumble chambers, and we have the spectroscopes. Okay, so these are the instruments that you can use in the laboratory to determine the type of radiation that is being emitted from a radioactive atoms. Examples of radioactive atoms, we've given them before, are the radium, the radium, and you also have some isotopes of thorium and all the others. There are very many. Okay, so generally they operate by this instrument, they operate by detecting either the alpha ray, the beta ray, or the gamma rays that are present in the particles that is giving out the radiations. Okay, so let's talk about briefly about the half-life. The half-life of a radioactive isotope is the time it takes for half its concentration to decay by half. To decay by half. The half-life of a radioactive isotope is the time it takes to lose half the amount of the radioactivity. The concentration of the radioactivity, when it is reduced by half, then we call that half-life. So each radioactive isotope has its own characteristics half-life. For example, the half-life of sodium-24, carbon-14, uranium-238 are well stated here. So each radioactive isotope of an atom has their own peculiar value of half-life. So the value of the half-life is independent of the amount of the isotope. So whether the isotope is 1 gram or 1,000 gram, okay, the half-life still remain at a specific value. For example, for sodium-24, the half-life is 15 hours. So each radioactive isotope of an atom has its own definite half-life. And there is what is called a radioactive decay law. So every radioactive decay is governed by the equation. And the equation is stated, the time count, which is the NT, is equal to the time count at 0 time, okay, exponential of minus lambda t, okay, where lambda is the decay constant. And that t there is the half-life. So the relationship between the half-life and the decay constant is given by the equation that half-life is equal to 0.693 over the decay constant. This equation is very, very important. The half-life, that is the T half, is equal to 0.693 over lambda. This equation is the equation for half-life of a radioactive decay. So please, you take note of it. It's very important. These two equations, N subscript T is equal to N subscript O, where the N is the count, the radioactive count. The radioactive time at time T is N subscript T. The radioactive count at time 0 at the very beginning, before the commencement of radiation, is N subscript naught. So you have N subscript T is equal to N subscript naught exponential minus lambda T, where I said the lambda is the decay constant, while the T is the half-life. Okay, now we've said there are 3 major types of radiations that are usually given out. We call them rays or we call them particles. They include the alpha, the beta, and the gamma. However, when we talk about radioactive decay, there are 2 major types of radioactive decay. They include the alpha decay and the beta decay. And when we talk about radioactive decay, what are we talking about? We are talking about the disintegration of the original nucleus to give out these rays that we're talking about. So the original nucleus is called the parent nucleus, and the product that is formed is called the daughter nucleus. So anytime we talk about the daughter nucleus, we are talking about the product that is formed from the parent nucleus, while the parent nucleus is called the original nucleus of the atom, which contains the original number of protons and neutrons. When an alpha decays, for example, during the transformation of the parent nucleus into a daughter nucleus, you have examples of that. that the parent nucleus will undergo disintegration as you have seen for uranium, for radium, and for uranium in the equations that you have before you. For radium, you have the mass number to be 226, you have the atomic number to be 88. By the time it undergoes disintegration, the mass number will now be 222, while the atomic number will be 86, which means that he has given out the alpha particles, mass number 4, atomic number 2, as you can see in the equation. So in a decay, the atomic number, that is the mass number, and the atomic number of the parent nucleus are reduced by 4 for the mass number, and the atomic number are reduced by 2 respectively in the daughter nucleus, which means when alpha decays occur, the parent nucleus will lose the alpha particles. So the mass number will reduce of the parent nucleus will reduce to 4, will reduce by 4, while the atomic number will reduce by 2 to give you the daughter nucleus, which is the alpha particle. Okay. Now, when beta ray decays, when you have a beta decay, okay, when the parent nucleus undergo radiation to give us a daughter nucleus, the daughter nucleus of the beta decay is the emission of the beta particle. And we've said the beta particle could either be an electron, a fast-moving electron, or a positron. In the two equations before you, what you have is the formation of the daughter nucleus from the parent nucleus. So in the daughter nucleus, you have a 0 mass number and you have -1 atomic number that forms the beta particle, which we call the daughter nucleus. And so you have an example there of lead. The mass number is 214. The atomic number is 82. By the time it undergo beta decay, it will lose beta particle. The mass number remains the same as 214, but the atomic number will increase to 83 because of the formation of the daughter nucleus, which is the beta particle. So in beta decay, the atomic number, which is the mass number of the parent nucleus, the atomic number of the parent nucleus is increased by 1, while the mass number remains unchanged. There is no change in the mass number, but the atomic number increased by 1. The reason is because for the beta particle, it has a 0 mass number, but the atomic number is -1. Because it's -1, it will increase the atomic number of the parent nucleus by 1. And so that has to do with the beta particle. So there are two major radioactive decay. We have radioactive decay, which is called the alpha decay, where an alpha particle is removed from the parent body to form the daughter nucleus. And for the beta decay, you have a situation where the parent's body will lose a beta particle in the course of radioactive decay. In this case, the atomic number will increase by 1, but the mass number will remain unchanged for beta decay. So let's quickly look at how we can make use of radioactivities, the application of radioactivities. Okay, radioactivity can be applied in the following areas. Number 1, it can be used to design the aircraft. It can be used for the detection of metal fatigue. It can be used for food preservation, where it can be used to kill all the bacteria that are present, and by so doing, the food is preserved. It's normally used for the treatment of cancer in the medical field. And that is what they call the chemotherapy, where they use radioactivity to kill the cancer cells in the body. So it's normally used for cancer treatment. It's normally used for food preservation. It's normally used for carbon dating, what we call radioactive carbon dating. If you want to find out the age of any dead materials of many years, you can use radiocarbon dating to find out the age of that animal or plant that is dead for years. And you can also use it for the preparation of artificial elements. You can use them for the preparation of artificial elements through bombardment of the parent nucleus with the alpha particles. Okay, let's quickly look at what is called nuclide fusion and nuclide fission. Nuclide fusion and nuclide fission. Well, in nuclide fusion, we are talking about the nuclei of very light atoms. When the nuclei of very light atoms are made to combine together to form heavier and more stable nuclei, okay, with the release of large amounts of energy, we call this nuclide fusion. We call this nuclide fusion. When you have large amounts of energy be given out when the nucleus of light atoms are combined together to give you the nuclei of a more stable atom, we call that nuclide fusion. So nuclide fusion is the source of energy of the sun. The source of energy of the suns and the stars that we have, when you look up the sky up there, the source of energy of the sun and other stars is the nuclide fusion. So in the sun, okay, at a temperature of 10 million degrees, you have fusion reactions that are taking place. Okay, you have fusion reactions that are taking. So fusion, nuclear fusion is the attractive energy production mechanism. It does not pollute the atmosphere, but it is a way of producing energy. So when light atoms are combined together to give you a more stable, heavier atom, large amount of energy is released. In that process, nuclear fusion is used for the production of energy. On the other hand, the process of splitting a nucleus, the process by which a nucleus is splitted is known as nuclear fission. So relatively large atoms, where you have large atoms such as uranium, such as plutonium isotopes, when you split them, okay, when you split them into smaller atoms, okay, as a result of bombardment with neutrons, it will now give rise to other smaller nuclei, which are radioactive in nature. So in this case, more neutrons are released and some energy is released, but the energy here is small compared to the energy of the nuclear fusion. So when small atoms come together to give you a more stable atom with large release of energy, we call that nuclear fusion. But when there is splitting of a large atom, okay, to give you other smaller atoms, we call that nuclear fission. So nuclear fission occurs when a nucleus of high mass breaks up to give you two or more nucleus or neutrons of lighter masses with evolution of energy. With evolution of energy. So in nuclear fission, the total mass of the fission product is slightly less than the total mass of the starting materials in nuclear fission. Okay, the difference between the starting materials and the materials of the product corresponds to the amount of energy that is released. So in nuclear fission, the total mass of the fission product is slightly less than the total mass of the starting materials. And the difference between that is because of the amount of energy that is released. So in any nuclear reaction, generally, the overall energy liberated or absorbed is what is called the nuclear reaction energy. It's what is called the nuclear reaction energy. So this nuclear reaction energy is usually the difference between the parent nucleus and the daughter nucleus. Okay, so when an energy is absorbed in nuclear reaction, we call it endothermic or endoergic. When energy is absorbed in a nuclear reaction, we either call it endothermic reaction or we call it endoergic. And when it is given out, we call it exothermic reaction, we call it exoergic. So briefly, let's quickly explain further the difference between nuclear fission and nuclear fusion. In nuclear fission, the bigger or heavier nucleus is split into the smaller nucleus. Okay, whereas in nuclear fusion, we have the lighter nucleus fused together to form the heavier nucleus. In nuclear fission, it does not require high temperature, but in nuclear fusion, extremely high temperature is required.
Sorry, sir. The slides aren't changing, so.
Yes, I'm aware. We don't have this part of the slide. We don't have this part of the slide. That is why I'm taking much of my time to explain that aspect. Once again, I want to explain the aspect of the half-life because it's very important, the aspect of the half-life. You know, I've told you before that the half-life is the time during which half of the atom of a particular radioactive isotope originally present to decay. The time taken for half of the atom to undergo decay or disintegration is what we know as half-life. At half-life, Nt will be equal to NO over 2. Nt will be equal to NO over 2. That is the original atom that is present of the isotope divided by 2 will give you the half-life. But the major formula here for calculating the half-life of any radioactive atom is equal to T half is equal to 0.693 over lambda. It is very, very important, very, very important. That equation is very, very important. And so please, you have to take note of that equation. That T half is equal to 0.693 over lambda. So that when you are giving any calculation at all, you should be able to use that for the calculation. Okay. So far, so good. Let me just recap for those of you that didn't join from the very beginning. And after that, we will now do some revision or some few questions under radioactive decay that you will come across. Okay, so very quickly we started by saying that radioactivity is basically a reaction of the nucleus. Radioactivity is basically a reaction of the nucleus. And you know, in the nucleus, we have protons, we have neutrons. For any atom to undergo radioactivity, the atom must be unstable. An example of such atoms that they are unstable are thorium, uranium, radium, plutonium, and so there are so many. And because they are unstable, they undergo the spontaneous disintegration so that they will achieve stability. And in the process of undergoing spontaneous disintegration, they will give out rays or particles. These rays or particles are classified majorly into 3. You have the alpha rays, you have the beta rays, and you have the gamma rays. Okay, so our normal chemistry, chemical reactions are not reactions that has to do with the nucleus. In normal chemical reactions, the nucleus is not affected. What takes part in the normal chemical reaction is the valency electrons of the atoms. Okay, and along the line, we explain what the difference between the chemical reactions and nuclear reactions are. And we also said that radioactivities are majorly classified into two. You have the natural radioactivity and you have the artificial radioactivity. The basic difference between natural and artificial radioactivity is that in natural radioactivity, it involves spontaneous disintegration of the atomic nucleus with the emission of particles. Whereas in artificial radioactivity, it involves induced disintegration. In artificial, you have to induce it for radiation to happen. But in natural radioactivity, you don't have to reduce it. It naturally takes place because the atoms are unstable. But in artificial, you have to induce it for disintegration to take place. And remember, I've said that in radioactivity, three major rays or particles are given out. The alpha particles, the beta particles, and the gamma rays. And we've said that the alpha particles are helium nuclides. And the helium nucleus contains four mass number, that is 2 protons and 2 neutrons. The helium nucleus contains atomic number of 2. So alpha particle is majorly a characteristic of the helium nucleus. They have a very low penetrating power. Okay, they only travel few centimeters in the air and they can be stopped by ordinary paper. Okay, then we also talk about the beta particles, that the beta particles are majorly either electron or positron. The difference between electron and positron is that the electron are negatively charged while the positron are positively charged. So either of them are examples of beta rays. But all the while, the one that we are used to is the electrons. And you know the electrons are negatively charged. They have mass number 0 and atomic number -1. Whereas for the positron, you have mass number 0 and the atomic number is +1. And so they have more penetrating power compared to the alpha particles, and they can be stopped by any metal foil. An example of a metal foil is the aluminum foil. But they have less ionizing power when it comes to comparison with the alpha particle. And we said the gamma rays, they are high energy electromagnetic radiation. They exhibit wave properties. They have a very short wavelength, but they have the highest penetrating power when you compare them with alpha and beta rays. So their mass number is 0, while their atomic number is also 0. So they have a 0 charge and they have a 0 mass. Okay, so we've talked about what is important, that is known as the quality factor. The quality factor is an expression of how dangerous a radiation is, how dangerous the particles or rays that are given out from radiation are. Okay, the higher the value of the quality factor, the more dangerous the radiation. So the quality factor is an expression of the danger of a radiation. If the value is high, then that means it is more dangerous. For example, what you have here, you have alpha ray. If, for example, this is an example. If alpha ray is 20, beta ray is 1, and gamma ray is 1, what this means, for example, is that the gamma rays, is that the alpha rays here, as an example, is more dangerous. Okay, so it depends on the value of the quality factor at a particular point in time. Okay, so we've explained that nuclear reaction involve the nucleus, changes in the nucleus of an atom, which involve the changes in the number of protons and neutrons. And we've also explained that it's different from our normal chemical reactions. Okay, so you have a lot of examples that we've explained, and we've said that this one is also equally very important, that radiations, alpha rays, beta rays, gamma rays can be detected or measured using some equipment in the laboratory. And this equipment include the Gigamuller counter, okay, the scintillation counters, the diffusion cloud chambers, the bubble chambers, and the electroscope, okay, or the spectroscopes. So these are the instruments that you can use to detect these alpha, gamma, and beta rays. Okay, so we've explained what radioactive decay is all about and how you can do the simple calculation using the two formulas that are before you. So we've said that there is what is called radioactive decay. When disintegration is taking place in a radioactive atom, we call it radioactive decay. And there are two major radioactive decay. You have the alpha decay, you have the beta decay. So the original nucleus, okay, of the atom is called the parent nucleus, and the product that is formed is called the daughter nucleus. And we've explained all that. And we've said that radioactive decay can be used for the preservation of food by destroying all the poisonous bacteria that are there. Okay, they are used for carbon dating. Okay, for geological specimen when you have to find out the age of animals and plants that have died for years. Okay, they can also be used for cancer treatment to kill all the cancerous cells that are in the body, which is called the chemotherapy. So what you use is radioactivity. So they can also be used to prepare artificial elements. Okay, so now, lastly, let's quickly look at some simple questions that are very important. Then we call it a day from here. The questions are: number one, which type of nuclear radiation is the most penetrating? I'm sure everyone knows which of the nuclear radiation is the most penetrating. Thank you. The gamma ray is the most penetrating. Another one is that which type of nuclear radiation has the highest ionizing power? Which of them has the highest ionizing power? Which of the nuclear radiation has the highest ionizing power? Thank you very much. Amos have answered, is the alpha ray. Peter have answered, thank you very much, is the alpha rays. So, which type of radiation is used to sterilize medical? Which type of nuclear radiation is used to sterilize medical instruments? Medical instrument, to kill all the bacteria in the medical instrument. Which type of nuclear radiation is used? Does anyone know? Which type of nuclear radiation is used to sterilize medical instruments? Thank you. It is the gamma radiation. Volker, thank you very much. Yes, Musa, thank you very much. It's gamma rays. And lastly, thank you, Chikeze. Thank you, it's gamma rays. Now, lastly, which type of nuclear reaction, nuclear radiation is used, can be stopped? Sorry, which type of nuclear radiation can be stopped by a piece of paper? Which type of nuclear radiation can be stopped by a piece of paper? Thank you. Thank you. Yes. Yes, thank you. Amos, thank you. Amos, thank you. The alpha particles. The alpha particles. Now, let me test you with this. Let me test you with this before we close. I want you to take a piece of paper, state the numbers and the type of particles that are emitted. State the numbers and the type of particles that are emitted to change aluminium. The mass number of this aluminium is 30. The mass number of the aluminium is 30. The atomic number is 13. The mass number is 30. The atomic number is 13. So the number, the type of particles that can be emitted from this unstable species that I've given you to the stable species. The stable species is aluminium, mass number 26, atomic number 13. What I'm saying is that you have aluminium, the reactant aluminium, mass number 30, the atomic number 13. That is formed is aluminium 26, atomic number 13. So tell me which type of particles and the number that is emitted to give you this aluminium 26 and atomic number 13.
1 alpha ray and 2 beta rays.
1 alpha beta rays. Thank you very much. Thank you very much. That is beautiful. That is beautiful. So that is where we'll stop today in our inorganic chemistry lecture. Beginning from next week, we'll have the chemistry lecture. And thank you very much, Tommy Lola. Thank you for the correct answer. You are going to be informed when you are going to have a test for this inorganic chemistry we have this week, possibly on Monday. You are going to get the information when the test will come up. And these are some of the questions that we are going to do on that day. Any question? Just start the question and explain to you. Quickly, any question? Okay. In the absence of any question, thank you very much. If you need further explanation, you can meet with the class rep. He will show you my office. We'll do more explanation, okay, when you come around. So thank you very much. Have a nice weekend and a great day. Stay out of trouble. God bless you. Thank you.